Hi, we are from Group 2 and today we are going to present the hydrogen production and bioelectrochemical system focusing on microbial fuel cells.
So Assalamualaikum, I am going to present about the introduction for microbial fuel cells. So what is microbial fuel cells? Microbial fuel cells, MFC, are innovative bioelectrochemical systems that harness the metabolic activity of microorganisms, either by substrate utilization, electron transfer, anode reaction, proton migration, electricity generation, and cathode reaction. It is to convert organic substrate into electrical energy. As the global demand for sustainable and clean energy sources continues to rise, MFCs present a promising alternative to traditional fossil fuel-based energy generation. These systems operate by utilizing electroactive bacteria that oxidize organic matter, releasing electrons that flow through an external circuit to generate electricity, while protons migrate through a membrane to the cathode, where they can react with an electron acceptor, typically oxygen. So there are some problems regarding the usage of MFC. The main problems were related to the implementation and efficiency of MFC technology, such as low power output and efficiency compared to traditional energy source, the need for effective electrode materials and configurations to enhance the performance, environmental impacts and economic viability of MFC in real-world applications, and the necessity for comprehensive assessments to understand the sustainability of MFC. There are two hypotheses can be made from this study. Firstly, the use of specific biocompatible electrode materials will significantly enhance the power output and efficiency of microbial fuel cells. Next, the integration of MFC technology with wastewater treatment processes will result in improved economic viability and reduced environmental impact compared to the conventional methods.
We move on to the past and present of microbial fuel cells. Let's begin with the history. The concept of MSC was first introduced by Potter in 1911, where he discovered the ability of microbes to generate electrical energy by breaking down organic compounds. Unfortunately, for much of the early 20th century, there were limited attempts to translate this fascinating discovery into practical application. Interest in MFC research at the turn of the century. Schroeder 2011 documented the significant milestones achieved over the years and highlighted the renewed focus on this technology's potential for energy and environmental solution. This historical perspective shows how MFC have progressed from an overlooked concept to an area of active research and innovation today. Now, let's look at the present. Microbial fuel cells work through a two-chamber system, as shown in Figure 1. The anode and cathode are separated by a selectively permeable membrane. Microbes in the anode chamber generate electrons, which flow through an external circuit to the cathode, mimicking a bacterial electron transfer chain. Current research focuses on four key areas illustrated in Figure 2, which reducing the electrochemical process, improving the performance efficiency, cutting operational costs, and scaling up system for practical application. In terms of real-world use, MFC are being explored for sustainable wastewater management and as a source of clean, renewable energy. These advancements show the tremendous potential of MFC to address both energy and environmental challenges.
There are four factors that influence the microbial fuel cells, which are the first one, design, operation, and configuration. The second one is the electric material. The third one, membrane, and the last one, influence of microorganism. There are four different types of configurations that is proposed in order to improve the efficiencies, which are single chamber, dual chamber, triple chamber, and also the stack chamber. Most commonly used chambers are the single and the dual chamber, and the performance can be improved by modifying the anode surface area by altering two factors, which are the conductivity and materials. And modifying the anode surface significantly improves the power generation and electron transfer. Anode is actually the engine in the bioelectrochemical system, whereas the electrochemical active bacteria will act as a biocatalyst and also oxidation and balance. Moving on to the electrode material. So there are a few characteristics that must be possessed by the electrode material in order for them to become suitable, which are high conductivity, anti-corrosive, biocompatible, chemically stable, high surface area, and also high porosity characteristic. An appropriate material allows the formation of biofilm in the anode regions, and the generated bacterial community should remain in contact with the anode surface. And if the anode material is not suitable, the electron may decrease, which eventually decreases the bioenergy production. So moving on to the third factor is the membrane. So the membrane is very crucial because it prevents the mixture of oxygen coming from the cathode and anode compartment, at the same time prevent the transport of oxygen. Depending on the variety of membrane, its properties and nature is the determining characteristic that increase or decrease the MFC internal load. For example, if there is a high internal load, it will lead to low performance of the MFC. The most common type of membrane used is the Nafion 117, and that could be used by polymembrane and an exchange membrane, and also the porous exchange membrane. So moving on to the last factor is the influence of microorganisms. So the microorganisms responsible to directly transporting the electron through the oxidation of the substrate. And the successful electron transfer only occurs if the electroactive microbes come in contact with the anode surface. And emphasis can be placed on the group of metal-reducing microorganisms such as the geobacters because it has a great potential. For example, the geobacter sulfuridescens can produce high current densities in MCS due to their metabolic pathways. And the other species that can be used is Pseudomonas, Protobacteria, and also Shigella.
The first example of bioenergy production from MFC is bioelectricity production. MFCs generate bioelectricity through the metabolic process of electrochemically active bacteria that oxidize organic matter. During this process, electrons are released and transported to the anode, creating an electric current. According to Poland, significant advancement in power density for MFCs has maximum values reaching up to 4.99 watt per square meter in optimized system. This high power output is attributed to improved electrode materials and configurations such as dual chamber setup and innovative catalysts. The efficiency of a microbial fuel cell is dependent upon variables including the types of electron acceptors and catalysts employed. The second example of bioenergy production from MFC is production of hydrogen. In MFCs, electrochemically active bacteria oxidize organic matter, releasing electrons and protons. The protons can be utilized in the cathode chamber to produce hydrogen gas when conditions favor hydrogen production. Specific operational conditions, such as the type of substrate and the microbial community present, significantly influence hydrogen yield. For instance, using substrates rich in organic material enhances the metabolic activity of bacteria that can produce hydrogen. According to Poland, the maximum hydrogen yield of approximately 438.7 mg per liter from MFC system. This output is significant for application where hydrogen is used as clean energy carrier. Hydrogen produced from MFC can be utilized in fuel cells for electricity generation, making it a valuable component of renewable energy system.
Microbial fuel cells, or MFCs, represent an innovative way to treat wastewater while generating electricity. They are bioelectrochemical systems that utilize bacteria to convert organic matter into electrical energy. Now I'll explain how this mechanism works step by step. First, in the anode chamber, bacteria interact with the organic matter in wastewater. They consume the organic material, breaking it down into smaller molecules. This biological oxidation process releases electrons and protons as byproducts. The bacteria essentially act as a tiny biocatalyst, driving the initial step in the energy conversion process. At the same time, carbon dioxide is also released as a part of the reaction. Next, these electrons are captured by the electrode in the anode chamber and flow through an external circuit to the cathode. This flow of electrons generates electricity. This is what makes MFCs so unique, where they convert the chemical energy directly into electrical energy without the need for additional energy input. Meanwhile, the protons released by the bacteria migrate through a proton exchange membrane, or PEM, which separates the anode and cathode chambers. The PEM allows only protons to pass, maintaining the separation of charges needed for electricity generation. When these protons reach the cathode chamber, they combine with oxygen and the electrons flowing through the circuit. This reaction forms water as a byproduct. The overall process not only generates electricity but also results in treated water that is safe for release into the environment. The main outputs of the process are clean water, reduced organic pollutants in the wastewater, and electricity. This makes MFCs a sustainable and energy-efficient option for wastewater treatment. So to summarize this, MFCs rely on bacteria, an anode and cathode system, and a proton exchange membrane to simultaneously clean wastewater and generate electricity. This innovative mechanism has a great potential to revolutionize wastewater treatment in an eco-friendly way.
In an MFC design, to monitor natural attenuation around groundwater plumes, the anode electrode of the MFC is placed at the plume fringe where there is maximum microbial activity. The cathode electrode of the MFC is placed in a clean aerobic section of the same well. The anodes are connected via a wire and electrical properties are monitored. MFC in this application harness the natural ability of microbes to transfer electrons during contaminant breakdown, generating an electrical signal that reflects microbial activity. In a recent study, MFCs were deployed at a former gas production site in Northern Ireland. This site, contaminated by over 150 years of industrial activity, provided a perfect testing ground. Researchers installed MFCs in boreholes across different zones, the plume fringe, the plume center, and an uncontaminated area. Electrodes are placed at different depths to allow the system to detect variations in microbial activity across the site. Using MFC, they are able to detect where microbial communities thrive. This area is where microbes are actively break down contaminants as oxygen from clean groundwater mixes with a polluted plume. DNA analysis confirmed the presence of key electrogenic microbes such as Geobacter and Disulfuromonodesi, which are known to play a major role in contaminant degradation. This validated the MFC's ability to pinpoint active zones of natural attenuation.
Next, there are three challenges of microbiofuel cells as a sustainable energy source, which are technical, operational, along with market and integration challenges. Let's start with the technical challenges. First is about low power output. Microbiofuel cells produce significantly lower power densities compared to other renewable energy sources like solar and wind. For example, research by Logan et al. 2006 shows that power densities often remain below 1 watt per meter square, limiting their use in high energy applications. Next, limited electron transfer efficiency. Microbes primarily rely on indirect electron transfer mechanisms, which are less efficient than direct methods. Improving this efficiency is critical for enhancing power output. Lastly, material durability and costs. High costs of key materials such as proton exchange membranes, for example Nephon, and platinum catalysis significantly raises expenses. Furthermore, these materials degrade over time, increasing maintenance costs and reducing long-term efficiency. Now let's look at operational challenges. In substrate limitations, microbiofuel cells require organic substrates, but ensuring a consistent and cost-effective supply is challenging. Readily, degradable substrates like glucose are not always practical for large-scale applications. Next is scaling issues. Scaling up from lab setups to larger systems introduces engineering difficulties. For instance, maintaining uniform microbial activity and managing biofouling are significant challenges. Finally, for the energy recovery efficiency, processes like substrate pumping and system maintenance consume energy, often offsetting the electricity produced, leading to low net energy recovery. Lastly, let's discuss market and integration challenges. For economic feasibility, the high costs of materials and system maintenance make microbiofuel cells less competitive with traditional renewable energy technologies. Then, there is the case of regulatory barriers. A lack of standard protocols and regulatory frameworks complicates the integration of microbiofuel cells into existing energy systems, slowing down their commercialization.
In conclusion, using a variety of substrate organic sources, MFC have become known as promising clean, self-sustaining energy sources that are mostly utilized for wastewater treatment. MFC have the capacity to remove contaminants and treat wastewater using activated sludge, all while producing bioelectricity. However, since their introduction, these systems have encountered numerous restrictions and difficulties: high internal resistance, unstable current, biofouling, low power output, and mass transport loss are the main drawbacks of MFC technologies. The main obstacles that MFC researchers must overcome are the high cost of electrode materials, scaling up to large volumes, and energy losses as a result of the conducting materials resistance in comparison to conventional systems.
That's all from us. Thank you.